Hello, I'm Nayoung from Kite and Mail, and I'll be introducing our work on a robot capable of proactive assistance through handovers for sequential tasks. Robots are already being widely used in static environments such as factories and other industries. In recent years, the focus has shifted toward the robots that interact with humans in various dynamic environments such as cafes and private homes. No longer are they required to only repeat pre-programmed tasks. Instead, robots need to understand humans and their environments and continuously assist humans based on the understanding. Previous work aimed to make robots understand humans by recognizing audio, pulse, movement, trajectory, and other environment factors. One research splits an activity such as assembling furniture into multiple small tasks and focuses on classifying each small task independently instead of treating the whole sequence of tasks. Some works deal with robot assistance for sequential tasks. For example, one researcher learns the sequence of assistance based on explicit input on preference of order of task execution. Another researcher assigns two types of work, collaborative and independent work, to a robot and focuses on scheduling the work to reduce cycle time. These kinds of work concentrate on the problem of specifically when to help in a sequential task. We aim to design a robot that can understand the actions of human performing sequential tasks and provide the appropriate assistance. Providing the detailed instruction for all tasks is difficult and is inefficient due to the diversity of possible task execution. Instead, we design an assistance system that uses a predefined general knowledge about the task. Our system consists of an action recognition module, an assistance selection module, and an execution module. The action recognition module recognizes the current action the human is performing and outputs the probability of each action. These are then passed on to the assistance selection module, which decides whether or not the robot has to help. Then uses the recognized human action, the predefined knowledge about the activity, and the current state of the environment. Finally, the robot performs the handover of the specified object to the human. Detailed explanation on each module are as follows. We use low-pass network to detect human action. For training, the cognitive module provided by the Facebook research is used as a pre-trained model. We collect about 30 minutes of videos for training. The examples of action levels are pour water, cut tomato, and add salt as shown in the right figure. Activities that consist of sequential tasks, such as cooking or assembling furniture, can be divided into order stages that are made up of multiple related tasks. For example, the tasks that make up a cooking activity can be divided into the stages preparing ingredients, combining foods, tasting and adjusting, and so on. In such cases, knowing which task and objects are related to which stage may be sufficient to assist the activity. In our system, we provide the robot with a cooking knowledge bank that maps each human action to a specific stage of activity and contains a list of objects that are related to each stage. For example, for the stage of preparing ingredients, the knowledge bank maps the ingredient bread, tomato, and cucumber as ingredients for the sandwich. Using the cooking knowledge bank, the robot can provide the appropriate assistance to the human performing a specific stages of activity. The recognized action is first mapped to a specific stage by the knowledge bank. Then the robot finds objects related to the stage. Finally, knowing the possible objects that it can hand over to the human, the robot chooses an object that belongs to the particular stages. When multiple objects are feasible to the stage, the robot chooses one according to the predefined order. To evaluate our system, we performed experiments on 2 cooking tasks with a total of 12 participants. During each experiment, the robot is required to help the human up to 4 times. The robot picks up an object and places it where the human can easily reach. We compared our system to 2 other systems. The first system is the command initiate system. In this system, the robot acts only when commanded by the human user. Using an Android app, the human tells the robot which object to hand over. The other system is a random choice system. The system is based on the situation when the robot does not understand human activities at all. The robot is programmed to continuously hand over any unused object randomly chosen. Here is a video of our experiment. First, in the random trial system, the robot does not understand the human is cooking an egg. It incorrectly delivers bread or a cucumber, which have nothing to do with cooking an egg, making the human wait until it correctly delivers the salt for humans to use. With the command initiate system, whenever the human needs a certain object, the human sends a command to the robot through the smartphone app. For example, after he is done cutting the tomatoes, he asks for the bread and waits for the robot to deliver it. Finally, with our system, the robot understands what the human is doing and delivers the appropriate object so that the human can simply continue his task. We can say that the robot automatically delivers the bread once it sees the human cutting the tomatoes. We evaluated our system based on two objective factors. The first factor is the human idle time, which is the time gap between the moment the human finishes the action prior to the robot assistance and the time they reach out for the object delivered by the robot. The second factor is the object idle time. This is the gap between the time the robot places an object in its designated space and the time the human grabs the object. As shown in the graphs, with our system, participants did not have to wait long for both task A and B. The human idle time of our system was the shortest among the three systems. Participants needed to wait just for around 5 seconds in task A and 10 seconds in task B on average, and this is significantly lower than the comparison system, which required longer than 20 seconds of waiting. This is because our system did not require participants to spend time sending commands or wait for the right object to be chosen. Furthermore, the robot started moving while the participants were conducting other tasks. Therefore, the human idle time of our system was the shortest of these three systems. The object idle time of our system is similar to that of the command initiate system as shown. For both systems, objects were left unused for around 5 seconds on average for each subtask. This is lower than 1/3 of the object idle time of the random trial system. Although the robot proactively assists the human in our system, the object idle time was similar to command initiate system. With the command initiate system, the human issues an order and grabs the object as soon as it is delivered, which is why the object idle time is minimal. Because the object idle time of our system was similar to the command initiate system, it is possible to conclude that our system efficiently assists the human. For both tasks A and B were completed, we surveyed the participants on their user satisfaction of each system. The survey was conducted on a Likert scale of 1 to 7, with 7 showing highest agreement. As shown in the graph, the user satisfaction score about the system performance and interaction quality was highest in our system, though the difference is not that significant. To conclude, we proposed a robotic system that provides assistance to humans performing sequential tasks through handovers of related objects. Through experiments, we showed that our system can effectively help humans by reducing human waiting time. We use just a simple rule-based algorithm with the knowledge bank to decide the appropriate assistant, but more intricate algorithms may be required to be robust against anomalies and unexpected situations. Furthermore, we require the mapping between human actions and the activity stages, which could be replaced by automated techniques such as an action segmentation. Through these advances, robots will be able to better understand human activities and provide assistance in various situations robustly. Thank you for listening.